So a little bit of background on Ulysses. So we know each other since a long time, since Zurich. He's actually a psychologist, and he's now at the computer science department. So it's a good sort of mixture, the type of stuff we like to do, like being engineers and we have this station, right? So he actually started his PhD working on the intelligent room data, right? Where he was working on this neural system, an artificial neural system with neurons, artificial neurons that spike and all of that, to make a room intelligent that would interact with the inhabitants. And this was for the Swiss exhibits that visited, like, I don't know how many, tens of thousands of people.
500,000.
500,000. Okay, so many bugs, I guess, and many crushes, but...
No.
No?
Uptime is 99%.
Okay.
It's a thing of pride.
Yeah. So the thing is, from there, he got interested into the link between neuroscience, neural systems, and actually artificial intelligence. That sort of evolved. He was in Barcelona, also the Universitat Pompeu Fabra, where he started working with artificial agents, where we had this immersive room. So it's like a cave on steroids. We had also an interactive floor with lights and things. But at that moment, we didn't have any proper tracking system. So actually, ANS was powering the cave, multi-user cave. And then we started having the first virtual avatars interacting with people. And now he's moved to Austin University. And now he's working, basically pushing this artificial intelligence concept on virtual agents yet further. So, don't have anything else to say. Just, thanks for coming here, visiting us, and being available to give a talk here.
Thank you. Thank you for the introduction. So, let's see. So I chose a fairly broad topic. The way I like to do presentations is just ask me questions. I don't have I have slides, but I don't need to get to the end of my slides. If anybody wants to discuss something, I'm happy to just stop and start a discussion. I think that's equally fun as just me reeling down my program. So the motivation really for me has multiple facets, but one of the facets is that in recent years we've seen a really an incredible development of virtual reality technology. I should play. Both in the terms of the devices, so we've all heard like the numbers now at which the head-mounted displays are being sold, the quality, yet a better one coming out, augmented reality devices, augmented reality technology on your phone now by default. You see a video here. This is real-time rendering in Unity. I didn't make it, but it's sort of the state-of-the-art what Unity can now produce in real time. And I think so game engines play a big part in this fact that virtual reality has become such an accessible technology that's at our disposition. However, as you can see, I left something out here on purpose, beyond the beauty of the rendering that you can see here, which is really this point here. Humans are very social animals. Often you find the definition as that this is the characteristic of humans, is their high degree of sociability, how much time actually humans spend interacting with other humans, just as we do now, how much time is going into that, how much energy, but also if you look at the brain, for instance, you can see that there's a lot of resources allocated to social signal processing, right? That seems to be a very important thing and something really that defines us as what we are. So what I want to show you is sort of this idea of adding that missing component in a way to this. So again, state-of-the-art video here to give you a bit of an idea where this hopefully is going when we're talking about these artificial social agents. So I'm using that term because I want to open it up in a way that it's not only necessarily computer-generated ones, it could be a robot. I work with computer-rendered humans because it's just a lot easier to work with. There's no nuts and bolts, and there's other issues, but it's just generally, it's just because it's simpler. And so this is state-of-the-art computer-generated humans. Again, this is real-time, what you can see here. And so when I'm talking about artificial social agents, I specifically mean that they are, well, they're computer-generated, but they also have a level of autonomy. That's really what I'm interested in. So it's a combination, if you also think of it as a branch of artificial intelligence, what exactly that ever means, but these entities are autonomous. They're not puppeteer, they're not a representation of a human, they're choosing their own behavior as they go along. And the way I see this in terms of application is that they can stand in for any social interaction where normally humans would interact with humans. That's the vision. We're not there, but that's the vision of where to take this. So for instance, just two examples here, soft skills. So the ability to interact with people, to integrate with people, to speak in public and so forth. These are becoming increasingly important. We still haven't seen a move into more like service-oriented industries. So people having these soft skills is very important. And that's something you can train with virtual humans. You can have a person that lets you practice in front of a virtual audience, for instance, or can give you feedback of your performance. Another thing which I'm quite excited about is mental health. Big challenge, all in society. And many of the interventions in mental health are based on humans interacting with humans, but they're not necessarily available. I mean, in the UK, we're just writing a paper. Victoria, who's a postdoc I'm working with, she's doing most of the writing, but we're trying to write a paper to make a case about using augmented reality in that case for mental health. And if we look at the number, how long it takes to get in, if you look at the triage and then how long it takes to percolate through the system. Right now in the UK, the goal is that you can get into therapy if you have an anxiety issue, for instance, within 6 weeks, right? That's very, very, that's very optimistic. The reality is it's probably not going to go like that. You go to a GP, then you get a referral, then maybe you get a letter, and then you get an appointment, and another, maybe a psychiatrist sees you and somewhere. If there's a spot in a group, then maybe you'll have group therapy somewhere a year down the line. Okay, so this shows you that there's a real need and an opportunity also to use these artificial social agents as a stand-in, as a service provider of sorts, because they are available 24/7. They are portable. You can basically take them wherever you need to be, so it's not a matter of going to a specific location. But important is also that they're unbiased, right? They're not grumpy, they don't get tired, they can be repeatable in their behavior. So this is basically what I want to, that gives you the framework in which I want to present my work. And I will talk about a couple of projects that I've done so far, and give you, it's really like a quick brush through without going into great details, because it's more like, so you get an idea of what we're up to, and then please, if you have any questions or think that this sounds interesting, just reach out to me, send me an email, and I'm happy to, have a further discussion on this. So, where are we now? You saw this beautiful rendering, right, of this human, this character. But the fact is, actually, this is really what's happening in the background there. It's puppeteering, right? It's graphically beautiful, absolutely amazing. That if you look at the skirts and the skin and the face, and of course, you will also see that there's very little happening in terms of manipulation, because that just tends to go wrong. But the key is this is all driven actually by a human, okay? And I'm interested in that, in replacing that human that is the puppeteer there in the background. That's the goal to which I'm working. And I will show you 3 projects on reflexive behavior, on personality, and on a breathing project that we're doing, which is the demo that we had just shown at the expat conference. All right. Any comments so far? All right. So, the first project I want to talk about is motivated by the observation that when we have a character on a screen, this character lives in a glass box. This character does not react to anything that happens in the world around it, neither in the sort of the virtual world nor in the physical world. So these characters don't have that sense that we have, that if something is happening and I make a noise, for instance, that you pay attention. So this is the motivation to develop this real-time reflexive behavior architecture, so that these agents can become aware of their environment. I'm going to say aware in quotes because it's not awareness equals consciousness kind of thing, but more in the sense like if you watch them behave, that you would think there is some relationship. I call that here the contingency through what they are sensing and their behavior. And that's especially interesting for characters that live in the shared reality space, which means augmented reality. In an augmented reality case where you really want to make or produce that illusion that something is rendered, that is computer generated, is actually part of the physical reality, then that entity should also respond to events in the physical reality. And they don't do that at the moment at all. So the idea is to basically have a base layer, so a plugin that you can put into these characters, and that allows them to have that loop between what is happening and their responses. So, example here would be a start to response. And so this is at the stage that there's some implementation of it, so I will walk you through some of these basic parts that we have implemented so far. And the key is that we are doing this, so we're splitting this as the first instance into something which I called endogenous reflexive behavior and exogenous reflexive behavior, which means I distinguish between what the source is of the stimulus. So endogenous means it's coming from within yourself. So it's not generated by the environment, it's actually generated within the agent itself. Compare that to exogenous, which is things that happen to the agent outside it. And given also the history that I have, the way I'm approaching this modeling is that it's a data flow oriented approach that takes some inspiration from control theory and from neuroscience. That means I'm fundamentally interested in internal structures of models and not only on a mapping of input to output with a black box. Okay, that's, for me, as a psychologist, is just not really interesting. What I'm interested in is actually what's the moving bits inside my model. And to give you an overview of what this looks like, is there a pointer any chance?
There.
I think the one for the...
I think that thing is
for the laser spectrum.
So which one?
Uh,
You're speaking.
I think that one.
No? Okay. I'll gesticulate. So this is exactly what I was talking about. So this is a structured model, and so it starts with an input stage, then we have two systems, our fast and slow response to external environments, and we have endogenous reflexive behavior like posture shifting and gaze. And so information really comes in and flows through this process in real time. So this is actually the actual implementation of the models. It's not just a diagram. This is done in, I use Simulink and MATLAB, which is a graphical programming environment which allows you to do exactly this, right? So you think of everything as a data flow. A signal comes in, you process the signal, you generate output. And that's exactly what happens here. And then, so what we have at the moment is we have an orientation towards the events that happen in the environment, and there's a dependency on what the sort of the quality of the event is in the environment. So I'm skipping some of that stuff because I just want to show you a little bit of the overview, but there's a paper on that if you want to read a bit more. So we have a rapid response system, so what we do is we get the onset speed, so this reacts to events that are very rapid, compared to an event that is very slow, let's say a swelling of a noise, compared to a slamming of a door. And this is always where it's a bit tricky because this sound works. So what you can see here, so this is the real-time data processing that's going on. And so we detect a rapid onset with this onset detector, but what goes beyond your just input to output mapping is that we bring in some principles, such as shunting, for instance. So what you see is that the character only reacts one time. It doesn't react every time you have a slam of the door, because that would not be what happens realistically, right? So it's a simple system in some ways, but if you want to take it to one level up, then immediately it becomes a little bit more involved. I mean, there's, for instance, a few of these robots out there, for instance, the Pepper robot. They have some of these capabilities, so if they look at things that happen in the environment, but for instance, they don't have an ability to have return of inhibition. That means that they pay attention always, again and again, to the same location, and that's something, for instance, that we don't want to have here. And so let's look at the slow response. See that, please. So what you can see is there's a slow response, and so unlike the rapid response, there's a valence now here, right? So that there's an emotional quality attributed to the signal. So this is the case that there's a phone ringing somewhere in the audience, but alternatively maybe there's friends that just came into the room and they're chatting, and then so what happens in this case is actually it's a bit hard to see, but it's supposed to smile. Okay. Conceptually, obviously these are videos, but the system is done, everything is done in real time. So there's no pre-recorded anything. The only thing is I'm sending a control signal, say, gaze in this direction, okay, wherever the sound is located in space. But everything else is real time, this is autonomy. This is an autonomous system that makes these decisions and processes the signals as time goes on. And here you see a few of these other dynamics. For instance, he doesn't just turn his head and looks forever, he looks and then looks back. So he does again, he loses a certain interest. He's not looking all the time because that would just not be what happens. He looks and then eventually he's looking back and then he will go back again revisiting this. And all of this is done by just signal processing logic. So there's no if statement in there. What I have is as soon as he reaches a threshold, the interest increases, and as soon as he looks, interest starts decreasing and he has basically lost interest, he's looking back to the front door. Well, in this case, because he's an audience member. All right. Okay, so this was just a really, really rushed sort of idea of what this is up, or what I'm up to with this. But I do think that this is really important to have this kind of layer and bring this kind of non-verbal basic behavior into these agents, because often they just usually don't have it. And I think we spent quite a large amount of time doing natural language processing and all kinds of higher level cognitive processes, when actually I think if you don't react to what happens in your environment, that is a showstopper. Yeah, it just seems like an entity is just not there. It's just mentally absent, right? So the next step is to do this with physical sensors, not with simulated inputs, and to go into, ideally into an augmented reality case where your agent here reacts and pays attention to its environment. Okay, are you ready for the next one? Can you give me a glass of water?
Yeah.
That would be fantastic.
I'll get it.
This one. Okay, so now this one is a bit, well, there's a lot of common ground with what you've just seen in the way we're thinking about the control logic and the way we're going about building an autonomous character, but we're moving into a different aspect that we're interested in. And specifically, what we're after in this project is to be able to build characters that you would attribute a certain personality to. Okay? So the character should, when you watch the behavior of the character, this should instill in the mind of an observer a specific point in this sort of personality dimension. I'm not using the word personality. It's a dimensional, so we're grounding this in personality theories, specifically in the 5-factor model, which is the most common personality model that probably all of you have heard of. In computer science, it's often referred to as OCEAN. So openness, conscientiousness, agreeableness, neuroticism, and extroversion. And so what we want to build is like, it's in some ways, it's a reverse engineering task, because you have to think of what statistics of behavior do you have to create in order for a person to attribute a certain personality type to the character. And why is this interesting? We see a clear use for this in making characters more appearing as an individual, so that not every character that you interact with feels exactly the same, like a copy, because that is definitely one of those things that can impair your sense of realism when you have these characters, that they're very predictable. Everyone you interact with would react in exactly the same way. So this sort of, if people detect repetition in behavior, they usually find out something that really compromises their sense that this is an autonomous entity. So that's one aspect, but more specifically we can also think about, for instance, if we talk about counseling, that we can adapt the personality of this virtual counselor to the personality of the human they're interacting with. So if you have maybe a more reserved person, then your virtual counselor would also be a bit more reserved. Or if it's an extrovert person, it will be the other way around, right? Or whatever is the best fit. But we want to have the ability to generate these different impressions of personality. And the good news is that there is quite a good body of knowledge, even though fragmented, but it's there, of people having done all sorts of experiments with people and afterwards, thrown in a personality inventory. So we have some idea of how nonverbal behavior is related to personality. And so this is largely the thesis of Miriam Saberi I was working with at Simon Fraser University. So it's her thesis, and she did all the legwork. So she really meticulously went through and was looking for all the papers we could find that allow you to make a link between personality and nonverbal behavior. And the system that she developed is called RealAct. So with a goal to have a real-time interactive system, again, this is not pre-scripted, things happen in real time, that allows you to give these different senses of personality. And so the way we're doing this is that we're having a real-time interaction between our virtual character rather than a screen here and the participant. So this is open loop. So we don't know exactly what happens. Of course, we define certain a priori responses, but all in all, we don't prescribe what the character exactly is doing. And what these two guys are doing with one another is they play rock, paper, scissors. So you know this famous game where one is the rock, one is the scissors or the paper, and you see that our participant is wearing a data glove so that we can track the fingers. So we need these three gestures, be able to track them with a high level of precision. So the participant and our virtual character, they're playing this game with one another, and then this is all, so there's no talking involved, it's just the way he's executing the non-verbal behavior, and all the interaction itself. Anything that needs language is guided over this monitor. There's a short video here, just to give you an idea of sort of what this kind of setup looks like. So we try to use it. The Kinect is still being used for measuring the distance of the participant to the screen. So if the participant goes too close, the character actually moves back. It wasn't good enough for tracking the fingers, so that's why we ended up with this high-tech data glove made of work glove and 3 bend sensors. And so just to give you an idea of how, so this is Miriam and she's interacting here with the character. So this is the actual experiment. It's a bit, so it runs a bit faster than normal speed to get a bit of an idea. So you see he has certain behaviors he's showing. It's like, you know, he's scratching his head, but it is mostly what we're after is that he's doing these gesticulations. But of course, everything he does flows into that impression that you form about the personality of the character. And yeah.
You said that on the screen.
Yeah. This?
Yeah. On the screen, you said that it supported somehow some aspects of language.
Yeah.
Can you give an example?
Oh, so this basically, because he's not speaking, right? So when it says go, that's when you're supposed to make the gesture. Instead of saying 1, 2, 3, you just have a go signal.
But it's talking for both. It's not the virtual.
It's basically what controls the flow of the game they're playing with each other. So it's just the way we get away with him having to do. I mean, it allows us to make this whole thing completely self-contained. So this is all hands off. There's nobody pressing any buttons. So this is really literally, participant go play the game, you say start and then you walk away. But we need something that adds that guidance through the game, right? That says, okay, now this next round and so forth. So that's, I think scorekeeping is also done. And so in the background we have a model that controls the entire behavior of this character, and that includes essentially an event-based system, which is a finite state machine, which we're using for doing the game control. So now in the state of that, now in the next state. So we're in different states, and then, but importantly, you also have an emotional continuous control system, which integrates the emotions and the affective state of the character over time. So this is a hybrid control system, and all of this has influences of the personality traits and goes into the behavior execution layer, which includes all the aspects, because you have to do all, I mean, you have to, there's not like, you can't just do one thing, not the other, right? So it has to have gaze, posture, facial expression, and the gestures. All of that is in there. And so just to give you an idea, so this is what it really looks like, not quite as clean, but here you would have the finite state machine in the core and the control system around it. There's scheduling involved and other aspects, of course, that make that this whole system comes together. So we have facial expressions and gaze, we have the postures, and we have, so these are 3 behavior controllers. Then he can do, the communicative behavior is when he's actually doing the gesturing during the game. He also just has your typical idle, and that's one of the things we want to improve. And the reactive, which is just basically he steps back when you get too close to the screen. And the important aspect of this conceptually is that we're not only just in a state from one state to the next one, like often you would sort of think of this in a sort of typical control implementation in computer science, but we have that internal affective state because it allows us to have that graded signal of the affective state of the character. That means, if you, for instance, as an example here, if the character is winning, sort of there's an increase in an internal affective state of, a positive internal affective state, and when he is losing, this state is going down, it's negatively affected. Okay? And this is really something that's quite difficult if you would think of this purely as a finite state machine kind of implementation. It's not a natural way of doing it that way, whereas if you think of it as a continuous signal processing, it's quite a natural way. And what it allows us to do is that we can control parameters of the internal affective states through our personality types. And specifically what we're doing is we have the idea that if you are a more stable character, effectively this also means that your internal affective states are much flatter than if you're an unstable or neurotic. So neurotic, this will be much more volatile, you react much quicker to winning or losing. So that's part of our personality model, because that's really what we're doing here. We're proposing a model. And then, but that's not explaining everything yet. Then we can have a second stage, which you can think of it as a gating, which then extroversion and introversion come into play. So depending if you're introvert or extrovert, that modifies the probability that you're actually acting out this internal affective state. And we did test this with 2 types of experiments. One was videos, where participants were just watching videos of the character behaving and then filling in a small personality inventory, and the other one was this real-time interaction that you have just seen. And so this is an example of the videos, so you have a bit of an idea of what it looks like. So I should maybe explain this here. So we use this 2-dimensional space, extroversion, introversion, neuroticism, and stability. So that's what these abbreviations mean. So HELS, for instance, is high extroversion, low stability. So we have the 4 points in the quadrant. So when you see those. So to go back to this, so here, low extroversion, low stability. Whereas on the other hand, we have a character which is much more volatile, but there's don't want to bore you with all the details. We have quite a detailed table how exactly, for instance, the speed of movement is affected, and the range of movement, and all these aspects that go with it. But the really interesting thing was the rock, paper, scissors, where we had the participant and the character play with one another, and we played a total of 5 rounds, 2 minutes each. So there's the 4 points in the quadrant and the neutral in the middle. So we have basically like a reference point. And basically, what happened is that we were pretty much able to achieve what we intended to. So how are we doing this? So how we do this is that we have parameter sets for each point in the quadrant that controls the interaction of the character with the human, and we can measure what the actual rating was that participants gave. So after each one of those 5 interactions, they were given a 10-item short personality inventory, and that's enough most of the time to get this. And we were just interested in 2 points, but to not make it too obvious, we gave them the full inventory, and then we look at how does what we have as our goal or target relate to the rating that the participants gave. So if we look at this, we can see that, so let's start here with the neutral. So the character tends to be seen as a little bit, so 4 is the mean that we see that character is considered a little bit introvert. And it was, I mean, the results are significant, but you can really see that the biggest increase here is to push up the level of extroversion. So really able to make the character seem more extrovert by setting the appropriate parameters. Whereas pulling down extroversion is harder, even though it still worked, but if you think about it, it makes sort of sense, right? Because like going down an extroversion is removing signals, so the character does less. And that's always harder to give an impression of things being absent as opposed to things being added to a system. And if we go over here, so this is the stability, so we have the target of low and high stability, that's what we measured. And so he seems a little sort of on the more stable side, but all in all the neutral is pretty much in the middle. And again, we're successful at pushing in either direction, but it's a little harder to make the character seem more stable than the neutral baseline than to make him look less stable. Again, kind of intuitively also makes sense, right? Like, less stable means he's more fidgety, right? Everything is like, he's acting fast, he's like touching himself a lot of the time. It's easier to give that impression than to make somebody look really calm. Okay, so all in all, this is basically what we found. So we're pulling up, or pushing up extroversion, pull down stability worked really well. The underlying thing is also really that people did hang in there. So this is 10 minutes where you have a real-time interaction with the character, and people engaged in that interaction. And that is actually, in and by itself, not that easy to achieve, because people can easily be thrown off by things that are just too strange, or the system can just go off the rails. But I guess by combining really this, on the one hand, finite state machine that guides the interaction from stage to stage with continuous control, we're able to really build a system that is quite stable and can maintain an interesting interaction between the character and the participants. All right, so let me finish off with another thing that some of you have seen already at the conference, which is a little bit of a different take on the idea of a virtual human and human interaction, but it shares that it's a non-verbal type of interaction. And specifically, what we're doing right now is that we're trying to influence the breathing pattern of a human using the breathing pattern of a virtual character. This is the idea. So this is what people refer to as entrainment. The idea that one oscillator is influencing the other oscillator. And the reason we're interested in this is because if you can influence breathing, you have a certain handle on things like relaxation. So breathing is one of the most commonly used techniques in, for instance, to calm people down. Just focus on breathing. And so we're trying to do this, but we're trying to do this in a more implicit way without having a person directly talking to you. And this is sort of the underlying notion is that this works, we know that this works from human to human. There is quite a big literature that shows you that when humans are interacting with one another, or even just in the same room, they synchronize at the physiological level. And we want to see if we can harness this idea in the interaction between the virtual human and a physical human. And so, what we started, the first sort of pilot we ran, was an open loop, and we just wanted to see if we have a character breathing at a certain speed and the human breathing at a certain speed, do we get an influence? So what we did was that, I'm going to show this one first. So we have the participant has a breathing belt, or two breathing belts, abdomen and chest. We measure the breathing rate with a Vitalino DIY physiology measurements device. That goes into a controller where we send control signals on the one hand to unity, so the character is in unity, rendered in, controlled in real time, and we're also manipulating the sounds, the breathing sounds of the character. So this looks. So it's a very simple setup in some ways. So you just see he's just breathing there. He's really not doing anything.
Sounds like bad weather.
Yes. So it's you have to be really subtle with it. It's an interesting sort of fine threshold where you have to get the system to sound. You can still audible without being over the top. The same is true for the chest and abdomen movements or the head movements. But the good news is we're doing this. These are just notes. So none of this is an animation. Everything is controlled in real time. So I literally just turn down the sound from the nose or the sound from the mouth or the amount that the mouth is opening. Everything I can control in real time. There's no need to go back to fixing an animation. And so what we've done so far is we have an experiment where the character is breathing slow, fast, slow, fast, slow, fast, and then we try to see what the effect is on the participants. And we have some first results that are going in a good direction, but well, it's work to be done, definitely. But we do think that there will be a good chance that this is something that we can influence the speed at which a human is breathing. Now, of course, this can only be the beginning, where we have this passive way where the character is basically just breathing at a set frequency. Where we really want to go with this is something that is called active entrainment, which means that the character is adapting its breathing frequency to the breathing frequency of the human, and then gradually can drag basically the human's breathing frequency along, and in that way be adaptive in the way we use the entrainment signal, not just sort of this, here's the signal, and if it doesn't work, it doesn't work. Okay, good. So that's the three projects I wanted to talk about. I just want to finish off by saying one thing. Maybe some people are also interested in sort of a less applied approach to this. And my work is sort of always in this duality. On the one hand, I have things like, for instance, a problem like we want to have a system that allows people to relax. Then we say, okay, We could build a breathing relaxation system, and we could use social agents, virtual social agents, as part of that mechanism. And based on this, we'll define a model that is a control model in the background of that character. But there's also the other aspect that I start off with a model, and I have a predefined model that I want to test, and really what I want to do is use these characters as a model embodiment. I'm always in sort of this duality. So today I'm mostly talking about sort of the top stream, but I do believe that just like what Sergey and I have done, you take a robot and you let a neuronal system control a robot, we can do something very similar with virtual characters. We take a control model, we take a psychological model, and we put it on the virtual character, and we test that model through embodiment on the character. So, other projects that I'm doing, I have done some work on gaze behavior and social status. Speech breathing, that's where the whole breathing thing comes from. So how the characters are breathing and speaking is interleaved with one another. Social-spatial behavior. I'm also pushing the agenda here on tools. So, because I think the graphical programming paradigm is very powerful to build these complex real-time control systems. So I'm also contributing in the form of blocks, that reusable blocks for building these control systems. And generally speaking, one of those things that I really find extremely interesting is work from, this is the guys from the Institute of Creative Technology. And so they are pushing the agenda on these augmented reality agents. So that you wear a head-mounted display, but there's this blend of the character with the physical reality. I really think that this is the way to go for these entities. Yeah. I just have some people I work with, especially in this project. So Sanobar is working, is my PhD student. She's working on the breathing relaxation stuff, and Steve was the PI in Vancouver, and Mariam was doing all the work for the personality stuff, and I worked with the other guys from ICT regarding the reflexive behavior. Thank you. Right. Anybody still alive? I know I talk a lot.
Okay, do we have questions for Ulysses?
If you make your agent too much like human being, isn't it like start ignoring people? Like you are talking about counseling.
Mm-hmm.
Consider your patient is talking too much. So your machine are like, okay, it's talking too much. Let's not care about it. That's like a human being do. Like you are talking about counseling in some point. And most of the thing is like develop, like ignoring something or like respond to something. So consider someone is counseling with a virtual agent. And as a human, if your patient talks a lot, you just start ignoring it. Like you are listening and you are not listening.
Yeah.
So how you will prevent this in a machine?
So you want the machine to ignore the patient?
No, how you will prevent it? Like it will still react to the environment, but it is still kind of not ignoring the patient. Because all of
I mean, the thing is, of course, a machine is not getting tired of listening, right?
Yeah.
So the good thing is that if you have the right sort of analysis tools to get important keys out of the speech, maybe you're able to have a more targeted intervention by paying attention to what exactly a patient is saying. But I don't think that there's like, a generic way of dealing with something like that. Right? I mean, the thing is, but definitely you would have to think that you can, if it helps a person to talk for 3 hours straight, then right now, like you say, it's hard to find a counselor just listens, or a friend or anybody listening to you for 3 hours empathically. The character can sit there and be empathetic to you for as long as, as it is needed. So it can actually do something superhuman in that way, and just be empathetic and listen and nod and say, oh yeah, tell me more about it. And if that helps a patient, then so be it. I mean, that's, you know, who are we to judge if that's what that person needs? Right now, that's not possible, right? Because his time's up, and then see you in a week, right?
I have a question. What do you think about the social impact of the human beings? So, I mean, we are a social person, but with the machines, they will go so improved and so enhanced that it's like, I don't care about humans anymore, I just want to the machine.
Yeah.
Do you think that will be a problem in the future? Like, to the point that we isolate ourselves just to the machines and stop interacting with real people?
Well, you know, I mean, if you look at how teenagers are now interacting, it's a lot of this embodied communication, right? A lot of it happens already, not anymore in a face-to-face communication. So maybe if you have at least the character, that's, you still have to get some face-to-face interaction, even if it's not a real human. It's hard to say where this is going to go. I mean, I think we're still a long way away of really being able to provide a complete replacement. But what we can do is we can at least provide for some people, like elderly people, for instance. You know, I mean, a colleague of mine, we're having these arguments because he thinks it's immoral. But I think it's not immoral, because if right now, if a person, an elderly person, thinks the cat is just understands every word he is saying, and that cat is just really important, we know that's not really how cats work. But if it does provide something to that person, I think that's morally completely justified. Now, if that is not a cat, but a virtual character, you know, I think if that adds benefit, is beneficial for the person, I think we shouldn't, like, we shouldn't keep that from people.
But isn't it like homeopathy? It's like, does not work, but it still people feels good, and people are still taking homeopathy as a medicine.
Well, you know, like, it depends, I guess, what you take homeopathic medicine for, right? So there's a large range in which is basically, it's a placebo effect.
Yeah.
So if a placebo works, it works. You know, like, some people have not needed surgery because they believed that some surgery was performed on them when it actually was a shunt, it wasn't real. But their pain went away, and, you know, it worked for them. I find that's perfectly acceptable. You really have to think from a user-centric perspective, right? It's not okay if somebody walks through the door with, you know, I don't know, pancreatic cancer, to say, well, I should try homeopathy. That I think is not okay. But if it's shown to be a relief for a person, it doesn't really matter whether chemically, as long as it doesn't cause harm, I don't think it matters. And this is, yeah, of course it's not real, but, you know, that's a philosophical question, right? What is real?
When you started the presentation, I recall a talk by Steve 5 years ago about early therapists to help military people from who are suffering from post-traumatic stress disorder. Do you have some data? If these virtual therapists had an impact in terms of suicide decrease, since this was 5 years ago?
I don't know. I really don't know. I mean, these three guys, Ari, Stefan, and Mathieu, they were at ICT at the moment, so yes. Same place, actually the virtual augmented reality, that is Skip, it's a video from Skip Rilson.
And they have lots of virtual humans,
pictures,
museum guides.
Yeah, I know. I don't know the latest numbers in terms of, you know.
I found the purpose, I found it a good purpose to get some populations need these kinds of approach.
Yep.
I thought it makes sense. In terms of UK, or say is 6 weeks delay. Also, might be a first approach. Do you compare the people undergoing standard psychotherapy and people?
Well, I don't have a system that I can run a clinical study with at this moment. I mean, I wish I had, but this is, you know, we're building these things up, right? And I think that's a bit, I'm not exactly sure what happened at ICT, but I feel like the project has gone a bit quiet. So I don't know, or maybe they're just, you know, publicizing it or what happened there. But it's because it is a tough challenge, right? And it's a tough challenge to people, to have people hang in there. Like it's okay to have like a 10-minute interaction, but to have a sustainable interaction where people keep coming back, maybe go back for an hour every week. I'm not even sure that anybody at the moment has a system that would have people really like keep going back and that we would actually be able to get that data. To my knowledge, in the field, I don't really see that. I mean, it's sketches and there's parts, but to have that, to have really a system that has that, you know, quality, it's extremely difficult. And you know, we've all dealt with chatbots, right? And we know that this is not, it's good and it does some natural language processing, but there's a big jump missing from that to a really sustained interaction that feels naturalistic. So it's still really somewhat ahead of us. That's why one of the things I'm interested in is not so much necessarily therapy, but companionship. So somebody who can just be there, be an empathetic listener, maybe just say, how are you doing? When you need somebody just to pay attention. Without really going into the therapy. I'm very, you know, being a psychologist, I'm very cautious about the term therapy.
No, I agree.
So I think that I don't want to claim that I can do any of this at the moment. It's a vision, but I don't have a system that does that. Period. You have a question, yeah?
Yeah, it's related to the first question. As humans, we are aware about the pass of time, no? And one of the examples that you were talking about was about the inputs of sounds. For example, the slamming of a door. And the character was different if the sound was repeatedly. But I was thinking that, okay, the decisions, since I understood, was based on finite state machines. So in this case, for going from one state to another is going to take, for example,
it's exactly not based on the finite state machine, just to clarify that. It's exactly not. So it's a continuous signal processing, right? So I detect an onset. When there's an onset of above a certain threshold, it triggers an orientation reaction. You could probably represent anything as a finite state machine. Extended finite state machine. Whatever. But I'm not using that paradigm. So it's a continuous signal processing. So don't go, it looks, of course, like it goes into another state, but the way I'm doing it in the background is a continuous signal processing, and I tune parameters to generate different behaviors. So let's say, for instance, how long it takes him to go back, or how quickly he loses interest is a decay parameter in my model. Right? So I see that like he loses interest, and I can control the time course of that variable. That's how I'm doing it.
Because also it gets me to another question, is that as humans, for example, if we are hearing that there is a strange sound, at the beginning we are going to be interested in it. And then after that, after a period of time, we are going to, hey, it's again, what's happening? It's something strange.
Yeah.
And again, and maybe we are going to ignore it. But maybe it's also to get frustrated, maybe to get anger for the sound. There would be a kind of way to do this kind of environment to affect to the character of the avatar?
So the goal when I'm building these systems is always to be as generic as possible. And everything is in that sense. So these models are they're reduced to very few parameters. So I'm trying to control this behavior and generate a wide variety of behaviors just with a few control parameters. That's really the idea. So I don't have to customize these things locally. So whether or not, whether it's, so a sound has a valence associated, so whether he's getting upset or finds it, fun, so he has a threshold at which he will start orienting, so that's an individual parameter. The attribution of the valence, the association of stimulus to valence is somewhat an individualized property, and then is the decay at which how quickly he uses interest. That's really all there is in there. So by tuning these parameters, you can generate wildly different behaviors without having to change the structure of the model. That's the key. Right? So if you have a finite state machine, you start rewiring things. I don't need to rewire things. The model in there is I try to ground it as much as I can in, at least some intuition about how a signal will be processed, and then parameterize it without then needing changes in structure.
Have you researched specifically whether these features, these human-like features, are increasing engagement and likability, and sort of perception of the characters?
Which ones?
So just you're like adding the reaction, adding different personality, adding
yes.
Movement.
Yeah. So I did run a study where I manipulated. The tricky part with this, of course, is that what's the reference point? Right? Mm-hmm. So I'm trying to stay away from what a lot of people are doing in the field. It's just to show something that's now rated on a scale from 1 to 10. How realistic is it? Because I don't believe that really works. So the way I did it is I broke the system by associating the wrong stimulus with the behavior and stuff like that. So I did it. There's not a one answer to it. So and some things really worked. It turns out if you have the character, for instance, looking back repeatedly, that increases realism. Other things, like for instance the association of valence with the response, that turned out not to be significant, that there's a more diverse sort of results coming out of this. So we still need to tune these parameters, and for instance the emotional expression and some of these aspects are, we need to fix it or improve it. It needs tuning.
But is the realness actually increasing, say, likability or desire to interact?
We didn't ask these things specifically in these cases because I guess because let's say for instance in the personality case we want to just treat it as if it was just a normal interaction, right? And we don't want to lift people too much into starting to think about it, especially if we do repeated measures, right? And you don't want to every time put it so much in the forefront to think about, so this computer-generated entity, would you know? So that's why we just treat it as, you just interacted with that thing, and now please fill in the questionnaire. So, but it's the big open thing in the field in general, is to find that good measure that goes beyond just a rate believability from 1 to 10. And I don't have the answer for that either, unfortunately. We'll get there eventually, but some behavioral measures, for instance, or brain correlates, so neural response patterns that go beyond just, because with rating there's always the problem. People just try to do you a favor, right? If you just show that one system, it's like, I made that system, do you think it's good? Rate it on a scale from 1 to 10. And we know what most of the time people are going to tell you.
Okay. Do we have more questions? Okay, maybe a last one?
Yeah. I want to know about some technical information, like you showed a game in which you got hand, and the game was written in Unity or MATLAB or?
Okay, so let's see. So the backend is MATLAB and Simulink, and the control signals go over ActiveMQ, so middleware, we're using SmartBody, which comes from ICT. That was basically the behavior realizer. So we sent BML commands, behavioral markup language, so like look there or now play the scratch your head animation or do this, gesture or move backwards. So we send these high-level control commands into SmartBody, but all the AI, if you wish, is all done inside MATLAB.
And there is no use of Unity in that.
So that system wasn't Unity, but I've moved into Unity. So now, the things we saw with the breathing, that's all done in, Unity plus an integration of a behavior realizer, BML parser. So I'm moving from SmartBody I'm in the process of re-implementing some of the functionality that I need inside, based on internal tools that Unity provides. Because Unity gives you so much now already in terms of IK and gaze control and animation control, that a big system like SmartBody is not, it's tricky to work with it because it's very big, and the 3D pipeline, the content pipeline, is not really that easy to work with either.
Okay, thank you very much. Thank you, Ulysses. So it is going to be around a little bit, right? Do you have your contact if anybody? Okay. Good. Thanks for coming.